We're going to consider the same scenario that we had in the last video. So we've got this bag with 5 red, 3 blue, and 2 orange chips in it. And I want to, again, answer the same first question here. What is the probability that the first chip you draw is blue? So the first chip is blue. So again, we want to think about the overall sample size. We calculated this out in the last one, but if I take all of these and add them together, I've got 5 red plus 3 blue plus 2 orange. I should end up with 10 in total for my sample size. So again, I'm imagining a scenario where I close my eyes, I reach into the bag, and I'm picking out one of these chips at random. The probability that the first one is blue, well, we just said that there were 10 total outcomes altogether, and then, well, we know that there are 3 blue chips in this, so 3 out of 10, or 0.3. Same answer that we had in the last video. Okay. Moving on to part B now. So now this says, suppose that you did indeed pull a blue chip on the first draw. So you did indeed pull a blue chip on the first draw. Again, this is my given. This is going to be a conditional probability here. So we're talking about a conditional probability where the fact that we know is that the first is blue. Continuing on, this says, if drawing without replacement, what is the probability of drawing a blue chip in the second draw? So this is a little bit different. It's kind of the same question. This is still asking the same question that we answered in part B in the last video, where I want to know what's the probability that the second is blue, given that the first is blue. But I've now changed the sample size because I'm talking about without replacement. When I sample without replacement, what that means is I started off with 5 red and 3 blue and 2 orange chips. And this is saying, suppose that the first one is blue, and I am not going to replace it, which means I take it out of the bag and I put it to the side, and I'm going to take another chip from the bag, but I have 1 fewer chip left. I don't have 3 blue chips. I now have 2 blue chips left after I've taken that out. So what this means is it changes my sample size. If I take 5 plus 2 plus 2, I've got 9 total this time around. So instead of dividing by 10, my overall total number of outcomes is going to be 9. I have this out of 9. So again, out of 9, how many of them are blue? Well, we said right here there are 2 blue chips remaining because I already took one out of the bag and I already set it to the side. So that there are 2 blue chips out of 9. Should be, I believe, 0.2 repeating, but let's just make sure. Yes, indeed. So 0.2222 to 4 decimal places. So when we sample without replacement, you cannot draw the same item twice. Yes, you could draw 2 blue chips in a row, but you can't draw the exact same blue chip because we've taken it out of the bag, we've taken it out of the overall population. We can't choose that individual again. So it's something that we're going to have to be a little bit careful of this time around. Moving on to part C, it says, suppose that you actually pulled an orange chip. So we pulled an orange chip in the first draw. Again, we are drawing without replacement. So let's pause for a minute. We pulled an orange chip in the first draw. We're supposing that, which means this is our given. Once again, we have a conditional probability. So the condition that we have is that the first chip was orange. We know we're sampling without replacement. What is the probability of drawing a blue chip in the second draw? So what's the probability that the second then is also blue? So again, I want to consider the sample size here. I started off with 5 red, I started off with 3 blue, and I started off with 2 orange. And this is saying I am sampling without replacement, so I'm going to take one away. And the one that I'm taking away is orange. So I'm taking away an orange chip. So I no longer have 2 orange chips. I actually only have 1 orange chip, which, okay, that's not going to change my numerator, but it still, again, does change the total number. If I take 5 plus 3 plus 1, I've got 9 total. So out of the 9 total chips that I have in my bag, I haven't changed the total number of blue chips from my initial setup. There's still 3 out of 9, but I have changed my denominator here. I have changed that sample size, which will in fact change my probability. So 3 out of 9, if I wanted to simplify that, that's the same as 1 over 3 or 0.3 repeating. So we'll say 0.3333. So what I'm noticing here, and this is the question I'm going to consider in the next part, it says, hey, if we're drawing without replacement, are the first and second draws independent? Meaning, does the outcome of the first draw have any effect on the outcome of the second draw? Well, here the first draw was blue. We ended up with a probability of 0.2222. Here in this case, in part C, the first draw was orange, and the probability of that same event, the second being blue, is 0.3333. So what I'm noticing here is that, yes, it does matter. Knowing that the first one was blue versus the first draw was orange changes that probability of the second draw being blue. So that does in fact matter. So that means that, no, they are not independent. So they are not independent. If you wanted to use a different word, you could say dependent. I'm not a big fan of that word when we're talking about this. You could also say they are associated or something like that. And the reason for that is the outcome of the first draw affects the probability of the second draw. And having that knowledge gives me some information. So that means that they are not independent, which means I can't quite use my general multiplication rule, but I can still use a multiplication rule that we talked about in the last section. So moving on then to part E, it says if drawing again without replacement, so without replacement, what is the probability of drawing 2 blue chips in a row? So again, when I say 2 blue chips in a row, this is really an and probability. I want to know what's the probability that the first chip was blue and the probability that the second one is also blue. Well, I can't just multiply these together because the probability of that second one being blue is going to change based on the outcome of the first. So I have to get a little bit creative. The way that I'm going to split this up is I'm going to say, okay, I am going to take the probability that the first is blue. That part's fine. That part has not changed from the last one. But what I need to multiply that by is the probability that the second is blue, given that the first was also blue. Oops, blue right there. I can spell. So you might do this intuitively, and it might seem silly for me to write it out, but I'm going to write it out this first time just so that we can see how we're coming up with these numbers. So the probability that the first is blue, we did that in part A. There were 3 blue chips out of a total of 10 altogether, and I'm going to multiply that by now the probability that the second is blue, given that the first is blue, and knowing that we are drawing without replacement. So without replacement, I've taken a blue chip out, which means 10 goes down to 9. There's only 9 chips remaining. And I've taken away a blue chip, which means instead of 3 blue chips remaining, I now only have 2. And then I would just go ahead and multiply these 2 fractions. So in my numerator, 3 times 2, I end up with 6. 10 times 9, I end up with 90. Oh, I believe those are both divisible by 6. Let me double check. Yes, so if you divide them both by 6, if you wanted to reduce that fraction, you could say 1 over 15, or if you wanted a decimal, that would look like, oops, let's give myself a little bit more room, 0.0667, or 0.06 repeating. So depending on whether you wanted a fraction or a decimal, that is your answer. Now, in general, the thing I want to end this video talking about here is that a lot of students tend to get confused about how we deal with and probabilities and how we deal with or probabilities. Or probabilities, I think, are a little bit easier because there's really not a whole lot of distinction between independence versus dependence. On the other hand, we do have to kind of consider mutually exclusive. When we talk about or probabilities, we know that the probability of A or B, we've said, is the probability of A plus probability of B minus probability of A and B. So in general, the thing that I always kind of point to is when we're talking about or probabilities, we're going to be adding and perhaps subtracting. It's going to depend on whether those two events are mutually exclusive or not. But in general, I like to think about or probabilities as we are adding, versus if I want to talk about and probabilities, probability of A and B, that was probability of A times the probability of B given A. So that kind of matters here, whether we're talking about independent events or dependent. If they are not independent, if they are dependent. If they're independent, then it's a little bit simpler. It's just probability of A and B is equal to probability of A times probability of B. But the thing I want to point at here is say that when we're talking about and probabilities, in both cases, regardless of whether we have independent events or dependent events, we are going to be multiplying. So this is kind of the rule of thumb that I give. Obviously, there's going to be exceptions to the rule. There's always exceptions to the rule. But in general, when we're talking about or probabilities, we're probably going to be using some amount of addition. And when we're talking about and probabilities, we are probably going to be using multiplication.